Okay, folks, let's get started. Can people in the back hear okay? Yeah? Okay. This is lecture number 28. Announcements. Homework 7 is due today. That homework party is over. Sorry about that. Yesterday afternoon I posted quiz number 2. Quiz number 2 you're meant to do on your own, but you're welcome to use any procedures that you wrote while working on your homework. You can use the interpreter to see if you got it right. You can use OK to check your work and to look at examples. But please leave yourself enough time to work through these problems. They're not simple. Question? Oh, man. I'm terrible at announcements. Okay. Quiz number 3, that's true. Homework 8 will be posted whenever I write it, and it will be due next Wednesday. Project 1, 2, and 3 composition revisions are due on Monday the 13th. And Project 4 is the thing you should really be thinking about. That is due 2 weeks from tomorrow. It's not something that you want to leave till the last minute. Questions about any of that? You heard from someone who told someone else that you used to get 3 weeks to work on this project. You got more than 2 weeks. I don't know if we ever gave a full 3 weeks. I like to round up. I think you get a normal amount of time. We did do quite a bit of work this semester to make sure that the project was less confusing. That doesn't mean it's not confusing, but it might be less confusing. So hopefully the amount of time that you spend just confused will be reduced. But I still think the project takes quite a bit of time just because it's long and there's a lot of concepts going on at the same time. If you finish the project and you want something else to work on, there is a optional but highly encouraged Scheme recursive art contest. It's one of those contests where kind of everybody wins, because what we're going to do is compile a gallery online of all the different contest entries, each of which is an image that you drew by writing a recursive Scheme program and interpreted using your own Scheme interpreter. One of my favorite parts of the course, but sometimes it can take a while to get your image just right, so I do suggest starting early. You can start on the recursive art contest just using the Scheme interpreter that we provided to you, if you don't want to wait until you're finished with your whole project. I'll show you some past entries just to get you motivated. Here was a winning entry from fall 2012 in the featherweight division. There are 2 divisions. The featherweight and the heavyweight division are separated by how many Scheme tokens appear in your program. Parentheses don't count, but every time you have a name or a number, that's a token. And I guess it's a little washed out on this screen. But if you want to draw that cool looking tree, is there any way to adjust the lights so the tree looks even cooler? Oh. Better. I guess that's all we get. Thank you. The heavyweight division gives you, so the featherweight division gives you up to 255 tokens. The heavyweight division gives you up to 2,047 tokens. Fall 2013's winning entry looked like this. That is some serious recursion. If you want to understand how this image was drawn, ooh, even better. I have invited the 2 people who created it to give an extra lecture tomorrow evening. So at 5 p.m. in 2050 VLSB, they'll teach you about what a ray tracer is, which is the technique that was used to draw this image, and they'll talk about how they made it run fast enough so that it finished before the contest was over. So if you think graphics are cool and you want to learn how all that works in the context of a scheme program, then come here tomorrow, and you'll hear the people who created this image. So what is this tokens business? No. This is how many tokens appear in the source file. So a token is like the plus sign or the number 12, and this is how long your original code was. But there was, so this is not a lot of code. You know, you can print it out on a couple of pages, but it takes a long time to run because it does a lot of recursing in both of these cases. Yes. Okay. Pretty pictures are over. If you want to turn the lights back on, it's time to learn something. Okay, so what we're going to talk about first is related to one of the problems on your project. It's the last problem of implementing the scheme interpreter, where you implement something called dynamic scope. And we implement this in the project so you understand the difference between dynamic scope and the kind of scope you're used to, which is called lexical scope. So the way in which names are looked up in Scheme or in Python is called lexical scope. And in lexical scope, if you want to know what names are available to you when you're writing the body of a procedure, you just look at the rest of that procedure. So the formal parameters of that procedure are names you can use, and also the formal parameters and defined names in an enclosing function, when you define one function within another function. Okay, so that's called lexical scope. We've drawn lots of environment diagrams to understand how all that works. And the way that works is that the parent of a frame is the environment in which the procedure that created that frame was defined in the first place. Dynamic scope is different. In dynamic scope, the parent of a frame is the environment in which the procedure was called. So different calls to the same procedure can have different parents of the frames created, depending on who called them. Now this is a reasonable way to evaluate programs. In fact, it's really useful because it can save you some typing. It turns out that for large programs, dynamic scoping is more complicated to understand than lexical scoping. So dynamic scoping tends to only be used in languages where you're only building small applications instead of really big ones. But it's an important concept nonetheless. So let me give you an example. Let's say I defined a function f, which took in x and added x and y together. So what's x? It's that. What's y? Well, I don't know. Let's say I also define a function g, which takes x and y, and calls f on x plus x. So let's say I now call g on 3 and 7. What happens? Well, in lexical scope, the parent for f's frame is going to be the global frame, because that's the frame that was active when f was defined in the first place. So I have a global frame which has f and g, which are two different procedures, one of which takes x, while the other one takes x and y. When I call g on 3 and 7, then I create a g frame with x bound to 3, y bound to 7. And then when g calls f, I create an f frame. And in lexical scoping, f's parent is the global frame. So x is bound to 6, and what's x plus y? Well, we look up x at 6, we look up y, it's not there, so we look in the parent, there's no y there either, and we get an error. Questions so far? Dynamic scoping says the parent of f's frame is g's frame because it was g that called f in the first place. So that means the body of f can refer to any names in the frame of the function that called it. Whoa, interesting. So the way we're going to implement this in your project is by saying there are two kinds of procedures. There's lambda procedures and there are mu procedures. Now this mu thing is something we just made up for this course, so you could distinguish between dynamic scope and lexical scope. Most of the time in a programming language, you have to choose one or the other. You can't intermix them, although sometimes you can. So here we're going to actually mix them together by having procedures that have dynamic scope. So that means every time I call f, the parent of the frame that's created for the call to f is going to be whatever function called it. Which means in this environment diagram over here, for f the mu function, it's the case that the parent of the f frame is f1, because that was the active frame when f was called. And that means when I compute the value of x plus y, I find x is 6 and y is 7, and I get the answer 13. That's called dynamic scope. So why is dynamic scope cool? It means you can write an expression with lots of names in it, and you don't have to say when you write the expression where those names are going to come from. It's up to the caller to make sure that all the names are set up in the right way. You set y to the value that y is supposed to be, then you call f, and f knows what to do with y. So it saves you the work of having to pass y in as another argument. It can just be looked up automatically. Question? So good question. Can Python use dynamic scope? I believe no. It's forced to use lexical scope all the time. If you want dynamic scope, you've got to write your own interpreter. Okay? The rest of this lecture is about the extra credit problem on the project. Everybody loves extra credit, so I assume everyone will love this lecture. Even if you don't do the extra credit, you are meant to know the concepts behind what's going on, so pay attention anyway. We're going to talk about something called tail recursion. So the part of Scheme that we've learned, we actually haven't learned the whole language because programming languages have lots of features, and I don't want to go through all of them. But we've learned a lot. And the part that we've learned is a functional subset of the language. Well, what functional means is it's a certain property of a programming language that describes the semantics of the language. So in a functional programming language, all functions are pure functions, except for maybe some input and some output. And therefore, you don't have the ability to reassign values or have mutable data types. Because we've seen many examples in this course where if a function changes one of its values by changing the contents of a list, then it's not a pure function anymore. And when you bind a name to a value, that's a permanent binding. With functional programming, you get certain advantages. If you don't allow non-local assignment or mutable data types, it's the case that the value of an expression is independent of the order in which the sub-expressions are evaluated. So when you write your interpreter, it doesn't have to interpret things in order. It can kind of mix them around, and you'd get the same answer no matter what. And that's important because that means you could actually evaluate different parts of the program in parallel or only on demand, and you'd still get the same answer at the end of the day. So it gives flexibility to the interpreter when you have a functional programming language. And, perhaps most importantly, you get referential transparency, which was this idea that if you had a program and you looked at an expression inside that program, you could replace it with the value of that expression, and nothing would have changed. You'd still have the same answer to your program's behavior at the end of the day. And this let us do things like memoization, which sped up our recursive programs a lot. Okay, so functional programming seems like a really good idea, but it's kind of annoying because there's no for statements or while statements. And I might be worried that just writing basic iteration is going to take a lot of memory. it's not going to be efficient anymore because I have to use recursion for everything. And isn't recursion inefficient? Well, it turns out that we can make basic iterative recursion as efficient as a while statement. And the idea of tail recursion is how you do that. So this is saving functional programming from something that you might dismiss because you think it's inefficient by making it just as efficient as a programming language that has while statements in it. Oh, I just talked a lot. Any questions so far? Okay, let's go into the details. Feel free to stop me with questions. Well, let's talk about a function called factorial, which takes in two numbers n and k, and it computes n factorial times k. N factorial is n times n minus 1 times n minus 2, blah, 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 all the way down to 1. 0 factorial is 1. That's just part of the definition. Okay, here's a definition of the factorial n comma k function. If n is 0, then n factorial is 1, and 1 times k is k, so I return k. Otherwise, I recursively call factorial on n minus 1, multiplying in n times k. Oh, that's interesting. So the idea is to compute factorial by just multiplying in each number, n, and then n minus 1, and then n minus 2, into this k value. So that by the end, what you result with, after all the recursion is finished, is k times n factorial, which you return. If this doesn't make sense, then neither will the rest of the lecture, so feel free to ask questions. So n some number like 4, and k is some number like 1. So what does this compute? 4 times 3 times 2 times 1, that's 4 factorial, and times 1. And the way it'll do it is it'll say 4 times 3 times 2 times 1 times 1 is 3 times 2 times 1 times 4 times 1. So it's moving the 4 over. And then in the next recursive call, it says 3 times 2 times 1 times 4 is 2 times 1 times 3 times 4. Moves the 3 over. And eventually you've multiplied in all of the 4, 3, 2, 1 into k, at which point you return k, and the answer you get is 24. Yeah, so if you just want to compute n factorial, then you'd pass in k is 1. Really the only reason k is around here is to help us keep track in the middle of recursion of what numbers we've multiplied. Yeah, that's right. Right, so what about functional programming and control statements? Functional programming basically doesn't have many control statements. Well, I mean, there's if statements and they have a particular procedure. But every call expression, you can evaluate the sub-expressions in any order you want. Yeah. So I guess there are some contradictions to what I said. Oh, excellent question. In what amount of time and what amount of memory does this run? Oh, I'll show you in a second. Any more questions about how this works? And just an example. This is just like the simplest thing I could show you that demonstrates all the stuff that I have yet to demonstrate. Just some way of computing factorial. Okay, there's some other way of computing factorial, which says start with n and k, while n is greater than 0, rebind n and k to n minus 1 and k times n, and then return k. This definition of factorial n comma k really does the same thing as the one at the top. During each iteration of the while statement, n is multiplied in to k. So k gets rebound to k times n, and then we rebind n to n minus 1, so the next time we go through the body of the while statement, we multiply into k whatever k had before times n minus 1, and then n minus 2, and then n minus 3, until we get down to n is 0, and we return k. These are two functions that do the same thing. However, they take different amounts of time and space. This is linear time because I make the number of recursive calls that is equal to n. The amount of space that's required is also linear, and that's because I have to create a new frame for each recursive call to factorial. And I'm not done returning from any of those frames until I finally reach the base case. What about this? Well, this also takes linear time. We have a linear number of iterations through the while body, but it only takes constant space. I have to remember what n is and what k is, and then I'm done. Because here, we replace the old values of n and k as soon as we don't need them anymore. Well, so I said they basically do the same thing, but all of a sudden this one's just worse, because it takes up a bunch of memory. Well, it turns out that's memory we don't need. The whole idea behind the topic of today, which is tail recursion, is how to save us from this theta n space when I write down a procedure that has an equivalent description as just a constant space while statement. How do you do that? There must be some fancy computer science trick. Well, there is. So, I'm not going to tell you the trick. That's why it's an extra credit problem. But I'll show you that it works, and I'll show you why it's important in the context of scheme programs, so at least you know why you're solving the extra credit problem that you're solving. Okay, so we want to get this theta n and this theta 1 to just be the same. It shouldn't matter how you write this. And this is supposed to be true of scheme. In the revised to the 7th time report on the algorithmic language scheme, which is the specification of the language, it's like been revised and then revised and then revised again. That's why it's the 7th power. It says implementations of scheme are required to be properly tail recursive. This allows the execution of an iterative computation in constant space, even if the iterative computation is described by a syntactically recursive procedure. What's syntactically recursive? Well, here is the scheme equivalent of the original Python function that I wrote down. It is recursive. It says factorial of n times k, which is n factorial times k, is k if n is 0. Otherwise, I recursively call factorial on n minus 1 and k times n. Same as what I wrote down before. This is supposed to run in constant space, even though it's syntactically recursive. And that's what it means for an implementation to be properly tail recursive. Yeah, exactly. So as the programmer, I don't have to worry about it. I can just write the recursive version. And the interpreter is somehow going to figure out how to run this in constant space. How are we going to do it? We'll eliminate the middleman. What does that mean? It means I'm going to create a bunch of frames like I always did, but as soon as I don't need a frame anymore, I'll get rid of it. And the definition of when I need a frame will change. And it's with the simple intuition that if all this frame is going to do is return whatever the return value of this is, then I don't need this frame anymore. I can just return directly to whoever called the middle one in the first place. Let me show you what I mean. Okay, so we're back in Python. We're define factorial. We're going to compute factorial of 4 times 10. So that's 24 times 10 is 240. How does that work? Well, we define factorial in the global frame. Then we call factorial on n is 4 and k equals 10. That recursively calls factorial on n equals 3 and k equals 4t. So we've moved the 4 down. Now we're going to move the 3 down to get 120. Now we're going to move the 2 down to get 240. Now we're going to move the 1 down to get 240 again. And then what's going to happen? Well, this is going to return 240. And so is this, and so is this, and so is this, and so is this, and then we'll be done. So let's go through it. Return value is 240, is 240, is 240, is 240, is 240. Finally, these all turn gray, and we're not using 5 different frames anymore. But back here, there was a moment when we had 5 different active local frames, and that was what was using up linear space in N. That was bad. Instead, what we'd like to do is just return this value 240 right back to here, skipping all this stuff in the middle. In the extra credit problem on the project, you just write code that forgets about all of these frames and returns directly from here to whoever called factorial on 4 and 10 in the first place. So easy. Huh? Yeah, so there's something important going on here, is that it has to be the case that returning from the last thing is all it's going to do is return from the second to last thing without manipulating that value in any way. If we do manipulate that value, we might need the old frame. The reason it's inefficient, because it uses too much space, is that you have to keep around the intermediate frames even though you're not going to use them anymore. So under the normal interpretation of the recursive function that we've been used to for the whole course, you have to keep around a frame until it returns. And here we're keeping around all these frames until they return. But we didn't really need them. Right, so none of these are closed. They're all active at the same time. And that's bad. It would be nice if only one of them was active at a time. As soon as we're done computing n minus 1 and k times n, and we call factorial, we shouldn't need the frame for factorial nk anymore. Okay. A procedure, call, that has not yet returned is active. We use up too much memory because we have too many different active procedure calls, too many different active frames. However, some procedure calls are tail calls. A scheme interpreter should support an unbounded number of active tail calls using only a constant amount of space. A tail call is a call expression in what's called a tail context. What's a tail context? Well, there's a bunch of different tail contexts. You just have to know them all. One is the last thing that you do in a lambda expression is a tail context. Since it's the last thing that you do, you're just going to return the value from that. Sub-expressions number 2 and 3 in a tail context if expression are also tail contexts. Because in an if expression, you evaluate the predicate, and then all you do is evaluate the consequent, or the alternative. You don't do anything with that value. So let's look at this definition of factorial. A lambda expression and a define expression are the same thing, as long as we have this complex version of define that has the procedure call notation after it. So the last body sub-expression in a lambda expression is this thing. This thing here is in a tail context, which means that this is also in a tail context because it's sub-expression number 3 in a tail context if expression. Now, I know there's a ton of definitions on the screen. Basically, the intuition is if this is the last thing you're going to do before you return, then it's a tail context. Here are some other cases. All non-predicate sub-expressions in a tail context cond form, or the last sub-expression in an and or an or a begin or a let. These are all different tail contexts. Okay, so when you're solving the extra credit, go back and look at this slide. The only thing I really care about you understanding right now is that in a function, the last thing you do is a tail context, and in an if the whole if is in a tail context, then the second and third sub-expressions are too. And that means you can just forget about the frame as soon as you make the tail context call. Because there's nothing left to do. Once you make the call, you're going to get its return value and just return that right away. So you don't need to keep around all the names that you have in the current frame. Okay, questions, and then we'll do an example. You want to like see it work so you believe me? Okay, see it work. Okay. This is the solution to your project. I'm only going to show you a little bit. Here, there's a part in your project that says, uncomment the following line to apply tail call optimization, which means to make your interpreter properly tail recursive. Okay, I was going to define factorial of n and k. And what's that do? It returns n factorial times k. And how does it do it? Well, it asks if n is 0, at which point it just returns k. Otherwise, it's going to recursively call factorial on n minus 1 and what? K times n. Okay, that's factorial, that's if, that's define. Right now I've commented this out, so I'm just writing an interpreter where eval calls apply, and apply calls eval, and eval calls apply, and that means I'm creating a new frame every time I make a recursive call. So when I run scheme, loading this file, when I run scheme, loading this file, and I compute factorial of 4, I get 24. Okay, no problem. Factorial of 10? Oh, that's a big number. Factorial of 100? Oh, that's a huge number. Factorial of 1,000? Uh-oh. It says maximum recursion depth exceeded. So it tried to evaluate recursively, 395 times, and then it realized this is just going too deep. I'm using up too much memory. I'm going to quit. All it's doing is calling the same procedure over and over and over again with different values. Okay, so it broke. However, if you solve the extra credit and uncomment that line, then it will be the case that any frame you don't need will be thrown away. Which means if you want to call factorial 4, you still get 24. Factorial 10, you still get, what is that? 3,628,800. Factorial 100, oh, that still works. What about factorial 1,000? Oh, that works too. Okay? What about factorial 10,000? Well, we're not using up extra space with each recursive call. So it might still take a while. We're not making it any more efficient in terms of time, but we are making sure that it still runs and doesn't run out of memory. And it took a while because this is just a preposterously large number. But the point is that using tail call optimization, we had no problem computing it with our factorial function and our scheme interpreter. Well, it really keeps going for a while. Okay. Yeah, we'll just get that started and come back later. It may have made my computer sad. Okay, so we're going to go through a bunch of examples of whether something's in a tail context or it's not. Because this trick only works when the recursive call is in a tail context. So let's think about the length of a list. A list comes in, you want to make sure you only use a constant number of frames as you're evaluating the length of the list. So a call expression is not a tail call if more computation is still required in the calling procedure. So linear recursive procedures can be written using tail calls if you just restructure them sometimes, and that allows them to run in a constant amount of space instead of a linear amount of space. So as a programmer, you do have to think about this occasionally. Okay, so here's a definition of the length of S. If S is empty, the length is 0. Otherwise, the length is 1 more than the length of the rest of S. This is not tail recursive because the recursive call is not in a tail context. How do I find whether it is or not? Well, I can look for all the different tail contexts. Here's one. The last thing, the body of the define, is always a tail context. So what about the if expression within that? Well, that has tail context as well. So this is a tail context. If this were a recursive call to length, we'd be fine. But it's not. It's a sum where the recursive call to length is one of the operands. And so after I compute the length of the rest, I have more work to do. I have to add 1 to it. And adding 1 to it doesn't actually need the frame, because 1 is a constant. But Scheme's not smart enough to know that. It only knows, oh, there's more work to do, so I have to keep it around the frame, just in case somebody asks me to look up a name in that frame. So there's more work to do after I compute the length. Therefore, this is going to run using a linear number of frames, linear in the length of S. However, I could rewrite this procedure in order to run in constant space. Here's how you do it. You define another procedure within it. In this case, I've called it length iter, which takes in not only the sequence S, but also a number n of the length I've seen so far. If there's nothing left to S, then the length I've seen so far is the length of the whole list. Otherwise, I recursively call length iter, this procedure here, on the rest of S, adding 1 to the number of things I've seen so far. So I just count up the number of recursive calls I've made. And in order to use this, I can evaluate length iter on S, starting with having seen 0 elements so far. Now down here, this is the last expression within the body of a define. So that's a tail context. This is the last expression in the body of a different define, so that's a tail context too, which means that's a tail context, which means the recursive call to length iter is in a tail context, which means this whole thing will run in constant space. Does the same thing as the procedure at the top, but it's much more efficient. Exactly 4 people nodded when I said that, so that's something. But maybe everybody else has a question. Maybe the people who nodded have a question. Who knows? Yep. So if your last line makes 2 different recursive calls, then it won't be tail recursive, because those will both have to be sub-expressions of some expression that combines them. So think about computing Fibonacci numbers. If you add together fib n minus 1 and fib n minus 2, both those fib calls are not in a tail context. I can't think of a way in which you could have 2 recursive calls that both occur and are both in a tail context. because that will always make a tree recursive process. That always takes more than constant space. So this only works for iterative sequence recursion. Yeah, mutual recursion, this is fine. So if A calls B in a tail context and B calls A in a tail context, then that will all run in constant space. Could this be done in a language with dynamic scope? Great question. I'm going to go with no. Things get complicated with dynamic scope. It's a little bit, okay, so if your recursive call is an operand, that's bad. That means you have a call expression with a recursive call within it, and that's never a tail context. There are other cases where it's not a tail context either. Like if you put your recursive call in the predicate of the if, that would be bad too. Because after you compute the predicate of the if, then you have to go and compute either the consequent or the alternative, so there's more work to do. Oh, it's done. Look at all those zeros. This is madness. All right. That's old. Okay. I was going to show you something. Oh, I know what I was going to show you. Okay, so let's say we're just computing n factorial now. And if I compute n factorial by just saying n factorial if n is 0 is 1, otherwise it's n times factorial n minus 1. This is not properly tail recursive because I still have to multiply after I compute the factorial, which means I need to keep the frame for n around. Even if I've already looked it up, I still might have more work to do, and Scheme doesn't know about that. Okay, so that means if I restart Scheme, even though I'm optimized, the way that I've written my procedure is problematic, and therefore, if I compute the factorial of 1,000, it will crash. So two things have to happen at the same time. You have to be optimized, and you have to write a tail recursive function. We're okay? Question? Tail recursive means the recursive call is in a tail context. Tail context means it's the last thing in your procedure, or it's within an if in the last thing in your procedure. Okay. Basically, this tells you how to solve the extra credit. The return value of the tail call is the return value of the current procedure call. Therefore, tail calls shouldn't need to increase the environment size, because instead of keeping around a new frame in addition to the old frame, just throw away the old frame and use the new frame instead. I showed you all my demos already, sorry. Okay. Yep. 5, 4, 3, 2, 1. Okay. Let's do some examples. Which of these will run in constant space? Meaning a constant number of frames for the function that gets called. I don't know. Think about it. Talk to the person next to you if you want. You have 2 minutes. go through it. What about this one? Well, we have the recursive call in the third sub-expression of the if. However, that if is not in a tail context. So this is a tail context, but this is not, which means that's not either. This thing is going to take linear space, not constant space. What about contains SV? Returns whether a sequence S contains a value V. If null S, return false. Otherwise, if V is the first thing in S, return true. Otherwise, look in the rest of S for V. This is a tail context, which means this is a tail context, which means this is a tail context. It's okay to nest ifs. This will still run in constant space. What about has repeat? Whether S has any repeated elements is defined as well. If S is empty, then no, there's no repeated elements. Otherwise, you look and see if it's true that the rest of S contains the first thing in S, where contains is defined here. And it's true. Otherwise, has repeat of the coder of S. Well, this is a tail context, which means this is a tail context, which means this is a tail context. What about this? So contains is not in a tail context, but it's not the same function as has repeat. It's an entirely different procedure, a tail recursive procedure, and therefore it will run in constant space. And then it will return, and then we'll run the whole thing in constant space. No problem. And what about fib? Well, someone asked about this already. Here we have a tail context, which is great, which means fib iter 1, 2. Well, that's a different recursive call anyway. So we never make a recursive call to fib so far. But fib iter here, is that tail recursive? Well, this part is, which means this part is. So far we're okay. But the problem is that right here, we have a non-tail context, which means this is not in a tail context, and this is indirectly a recursive call to fib iter, because fib calls fib iter and fib iter calls fib. So this is non-tail recursive mutual recursion. This will not run in constant space. You can't write a tree recursive function to be tail recursive. You can write fib so that it's not tail recursive just by, so that it's not tree recursive just by remembering the last two numbers. And so that's how you'd write it to be tail recursive. Any iterative process, anything you can write using a while statement, you can write using tail recursion. Okay, that's enough for today. There's a couple more examples if you want to watch the videos online. I'll leave it up to you.